Good morning here, guys. Just trying to get a little bit of more information to you. We're doing some shear wave stuff now. We've kind of made that transition from compressional beam, or making that transition from compressional beam into shear wave. So I wrote up some shear wave calculations, which you guys are messing with this week if you haven't got to them already. Just kind of wrote out one example of each and then want to show you where that comes from. So if you see a V path, if you see a one leg, if you see a skip distance, you're going to be looking at, or what you're actually visualizing is this over here. Okay, get you zoomed in a little bit, where now we've got a skip distance, one leg, and a V path. So if we move up here a little bit closer, back out just a little bit, you're actually seeing what we just wrote over there. If you have a skip distance, if you're thinking of inspecting a weld plate here, okay, don't mind my crude drawings, but if you're thinking of inspecting a weld plate here, you're going to have a shear wave transducer, you're going to have the weld plate itself, and then you're going to have sound bouncing around inside of there, and you need to know where it's going. So, if you place your transducer out here, just somewhere, it doesn't matter right now the distance between the transducer and the weld. Place your transducer down there, and if that plate happens to be 1 inch thick, you're going to have one leg, okay, what we like to call one leg, meaning one sound path from that transducer headed towards the bottom of the plate, and that leg is going to be 2.92 inches long, and we'll go back to the calculations in just a second. Then, if that leg bounces, it's going to come back up towards the top again, and it's going to be another 2.92 inches long. Okay? Both of those added together is going to give us a 5.84 V-path, and let me write that up here. V-path 5.84 inches. Meaning, sound came out of the transducer, followed itself down, or made its path down, hits the bottom of the plate and bounces, and comes back up to the surface again. That all happens within 5.84 inches. So if we were viewing that on our CRT or our A-scan, if that was 0 over there and this was 100%, let me make sure you guys can see that, which you can't. So let's come down a little bit. Okay, if you were viewing that on your CRT, you would see 0%, 100%, which when you inspect a shear wave, you've seen on the video, when you inspect a shear wave, okay, your initial pulse is actually off of the screen over here somewhere. So we'll get rid of it. Okay, so it's out here in space. There's your initial pulse. Can't see it, or at least most of it. And then out here, if this is a 10-inch screen, this represents 0 inches, this represents 10 inches. A V-path of 5.84 would be somewhere over here if there was a reflector right here, right on the surface. Some reflector. I'm saying reflector instead of defect because you don't know if it's a defect yet. So, you have your 1 inch reflector, or sorry, your 1 inch plate, and then if it so happened that at 5.84 inches at the end of this V-path that there was a reflector, you would see a signal somewhere over here at 5.84. Now, which more than likely, when you're doing your shear wave inspections, there's not going to be many defects out here in the plate somewhere, but it can happen. So, leg bounces down, or leg travels down, bounces back up, and then once it hits over here, it's going to bounce back down and go this way, and it's going to continue to go back and forth. So we're going to have leg 1, leg 2, leg 3, 4, 5, 6, 7, 8, however many legs it stretches out. Generally, first to third legs is good. So we're going to take this transducer and we're going to move back and forth like this. Okay, and that's going to push this sound back and forth through here. But anyways, if we're looking at this, trying to figure out what these signals or what these waves actually mean, we know that shear waves coming down, shear waves bouncing back. So, from one V path, meaning where the sound enters a part to where the sound hits the top of the part again, that distance along the surface now is called a skip distance. And if we were trying to figure out where that sound actually is, we would put a transducer right here, beam exit point. We'd go straight up from our beam exit point, go straight across the plate, come straight down, and that's where the sound should be exiting, or would exit the part if there was another transducer there to pick it up. But since there's not, we're just looking for this distance so we know where the sound enters, where it bounces at the bottom, and then where it's going to bounce again at the top and head back down. That way, we can control our distance away from the weld. Okay, if we put the end of our skip distance right here, and we move our transducer back like this, okay, where our skip distance is right there, if we move this transducer forward, okay, there's a rudimentary transducer. If we move this thing this way, then you're going to see this sound beam move this way. Okay, so we started here, we're pushing it through, we're inspecting this volume of the weld here, okay, along with all of this through here, and then it presses on through. Okay, we missed this area, okay, and if we keep coming through, we're going to see this first leg come down here and inspect this volume, but we're going to miss some of this down here. So then we turn around and come back from this way to get the sound to bounce in, so we can pick up this area, and then we keep coming through so we can pick up that area. So got to inspect it from two sides, but really what we're concerned with is if we have a V path here, okay, where's the sound entering, where's the sound supposedly exiting? So along the surface, that would be from here stretched out over to here. In this case, it's going to be 5.49 inches. Now, how did we get to that 5.49 inches? We went back over here to these calculations, which we can move you over here. I know I move you around a lot, but at least you can see what's going on. Let's back out a little bit. Alright, so that tells us this. If we did a V path, if we calculated the V path for that plate over there where we just were, that would be 2 times thickness divided by the cosine of our angle. Okay, and the angle in this case was 70 degrees, and you saw that on the transducer over there. So 2 times the thickness of 1 inch divided by the cosine of 70, you should get 5.84 inches. Okay, half of that, which is 1 leg, would be the thickness divided by the cosine. So 1 divided by the cosine of 70, that's where we got our 2.92. That's 1 leg each. So 1 leg travels down, 1 leg travels back, all that good stuff. Then, a skip distance to figure out where the sound is when it enters and where it is where it's bouncing at the end of a second leg. Would be 2 times the thickness times the tangent of the angle. Okay, so 2 times 1 times the tangent, 5.49 inches. Okay, so let's just look back at that just for one last glance here. And you're seeing some of that right there. Skip distance of 5.49. You got leg 1, leg 2, and all that good stuff. Some horrible drawings. But if we come back here kind of to the center, somewhere like right in there, you're going to see on your A-scan screen, okay, if we had A-scan again, CRT, 0 to 10 inches in this case, at 5.84 inches or roughly 6 inches we'll say, that's 1 V path. That's where the sound enters, comes back, and bounces. So this would be leg 1 and leg 2. So from here, from 0 to 2.92, meaning roughly 3 inches, this is leg 1 information. So if you have a signal that bounces up in here, you know it's in leg 1. And then if you're going from 3 to 6, you have a signal that bounces up in here, you know you're in leg 2. Okay, then you go from 6 to 9, then you've got leg 3. Okay, 9 to 12, so on and so forth, and leg 4, leg 5, so on and so forth that way. That's kind of how you're looking at that. And some of the scopes, USN 60s and stuff like that, will separate out leg information so you can tell exactly where those defects are coming up. But if you don't have one of those scopes, you need to be aware of, on the A-scan, from 0 to 3, in this case, leg 1, from 3 to 6, leg 2, 6 to 9, leg 3, so on and so forth. And you can do that for any thickness. If your plate's only 375 or 3/8 of an inch thick, you can calculate that out and would be able to tell exactly on your screen where all that information is coming up. Okay? I guess it would have helped if you could have seen that. So let's go back down here just one more time. Okay, here's your 0 to 3, leg 1. Here's your 3 to 6, leg 2. Here's your 6 to 9, leg 3. 9 to 12 would be out here off your screen, leg 4, leg 5, leg 6, all that good stuff. So, just basic information. Leg 1, leg 2, this would be leg 3, leg 4, on out, so on and so forth. So if we get rid of all of that, you would have leg 1 from 0 to 3, leg 2 from 3 to 6, leg 3 from 6 to 9, leg 4 from 9 to 12, all that good stuff. Okay? Any questions? Feel free to email me, call me, whatever. We'll get you taken care of, and I hope you had a good week.